dt all along the path is basically the same thing as saying angle momentum. Everybody good with that? Alright. I'm going to go up here for a second and point out to you that I can solve and get d theta dt is L over mr squared. We'll make the whole on. Alright, so okay. This is something that's actually in Thomas More, rather's book, 6 Ideas of Physics, which we used to use, teaching 2.3, 2.4, or something. And I think it's a super cool calculation, so I think you should know this calculation. So, we want to use coordinates r theta. So here's the theta coordinate, here's the r coordinate. Here is the r hat direction. R hat is a unit vector. It means its length is 1. Everybody look at r hat and agree that this r hat vector's length is 1. Square cosine, square sine, add them up, get 1. We're good? And it makes sense, right? So if r is pointing off this way, the x component would be the cosine of the angle, the y component would be the sine of the angle. Theta hat is perpendicular to r hat, which means it looks like this. And if you work for a little bit, you can figure out that theta hat is minus the sine of theta cosine of theta. And one thing that you should notice, of course, is that r hat dot theta hat is cosine theta times minus sine theta plus sine theta times cosine theta is equal to 0. Why is that obvious? Because they're perpendicular to each other. Right? Flappy? Sure. Now, r vector dot is r dot r hat plus r hat dot. Because our object may not be going in a circle. So if you're moving along, and you're going to take the time derivative of your position vector, you got to treat r hat like a product, so you use the product rule. Everybody happy? R hat dot is d by dt of cosine theta sine theta. Okay, so now I'm going to use the chain rule. The derivative of the cosine is minus the sine. And the derivative of theta is theta dot. So the time derivative of the cosine of theta is minus sine theta, theta dot. Everybody happy? Good. The derivative of the sine of theta is the cosine of theta, theta dot. So if I look at r hat dot, it's equal to theta dot, pulling that out front, multiplied by minus sine theta, cosine theta, which is theta hat. So r vector dot is r dot r hat plus r theta dot theta hat. Good? Alright, let me take another time derivative. R vector double dot. That is otherwise known as the
radial acceleration.
No, it's the total acceleration. So R vector is the total position vector. So R vector double dot is the acceleration vector. Okay? Now having to write it in radial and theta coordinates, we're going to see what that comes out to be in a second. So now I've got two terms that are added up, and I got to use the product rule. And so I get r double dot r hat plus r dot dot plus r dot theta hat. Plus r theta double dot theta hat plus r dot plus r theta hat dot. First two terms are from taking the time derivative of r dot r hat. Last three terms are from taking the derivative of r theta dot theta hat. Theta hat dot is equal to d by dt of minus sine theta cosine theta is minus cosine theta dot sine minus sine theta dot. So theta hat dot is minus r hat theta dot. Okay, so I've got a bunch of terms here. I've got an r hat, another r hat, right? I've got a theta hat and another theta hat. I'm going to group up the r hats and group up the theta hats. Oh, and here I've got an r hat dot, right? So that's actually a theta dot theta hat. My side. You good? So I'm going to substitute everything in, and what I'm going to get is A is r vector double dot is r hat r double dot minus r theta dot squared plus theta hat 2r dot theta dot plus r okay, so you do a little bit, so you just plug in for r hat dot and theta hat dot. You collect up terms, and this is what you get. Not going to be hard out. You'll see it. Sit down. Or you look at the notes. It's all fun.
Is that r double dot minus r dot
Theta dot hat.
Theta dot.
R theta dot hat. Move my dot over.
Is that squared?
Square. Okay, now, I want to prove to you that this term is 0. L is m r squared theta dot. L dot is 2m r dot theta dot plus m r squared theta double dot is m r times 2r dot theta dot plus r theta double dot. And since the angular momentum is a constant, the time derivative of the angular momentum is 0. So the quantity 2r dot theta dot plus r theta dot double dot is 0. So that term is 0. Hooray! You good? It sure as hell better be 0. Why?
Momentum is conserved.
Yeah, momentum's conserved, but I need to use this now. I just found a formula for the acceleration
Oh, because then we would be moving like faster and
in the angular direction. You don't want to have an acceleration in the angular direction. Why do you not want to have an acceleration in the angular direction?
that would suck for us.
Because you never stop. It's just your speed increase.
No, physicists. Why could there not be an acceleration in the angular direction?
There's no force in the angular direction.
Because there's no force in the angular direction. The force vector is ma vector.
That's what I meant.
The force vector is minus g m over r squared r hat. The direction of the acceleration and the direction of the force need to be the same. That's Newton's second law. Since the force is radial, the theta hat term better go away. That makes sense? So if I take my formula for the acceleration and stick it into Newton's second law, multiply by m, I have m r double dot plus r theta dot squared. R hat is minus g m over r squared r hat. So here is my application of Newton's second law. But I'm going to be slick now. I told you to remember that theta dot was L over 2m. Up here. No, I told you. Remember that theta double dot was L over mr squared. So what I have is r double dot plus r times L squared over m squared r to the fourth is equal to minus g m over r squared, or r double dot plus L squared over m squared r cubed is equal to minus g m over r squared. So here I have, okay everybody, we're ready? A second order differential equation, woohoo! Go physics! Which is about as ugly looking as they come. This equation is nonlinear. It involves 1 over r squared and 1 over r cubed. It's just ugly. Ugly. And I lost a minus sign. There's a minus sign right here, which I didn't write right here.
Okay.
Now, yeah.
I have a question. This wouldn't be homogeneous then either, right?
It is, well,
Because if you add
I can write it all on that side,
and then it becomes homogeneous.
and then it would become functions of r and r. Yeah, okay, technically this is homogeneous.
Okay.
But once it's non-linear, you don't really give a shit whether it's homogeneous or not.
And this isn't linear because of r squared and r.
He's got 1 over r squared and 1 over r cubed.
Okay.
Linear means it only has r to the 1, not r to the minus 1, not r to the minus 2, certainly not r to the minus 3. Okay, so we are now going to prove Kepler's first law. Ready to go? It turns out that our problem is not that our differential equation is ugly. Our problem is that we're looking at our differential equation the wrong way.
Let's
We need
change
beer
the
gardens.
coordinates.
So let's define u to be 1 over r. What was that, Dirk? Okay.
Change our coordinates, right?
Yeah, we're going to change coordinates. And instead of d by dt, or dot, use d by d theta. Okay, now, so dr dt is equal to dr du, du d theta, dt. Okay, and if r is equal to u to the minus 1, because u is 1 over r, so r is 1 over u, then dr du is equal to minus 1 over u squared. Theta dt, we learned, is L over mr squared. So d theta dt is L over mr squared is L u squared over m. So, hey look, this u cancels that u. So if I'm going to take d by dt now of dr dt, so the second derivative of r respect to t squared is d by dt of dr dt. Dr dt I just found out was minus L over m du d theta. But d by dt I'm going to write as d theta dt d by d theta. So d by dt is L over m r squared. So d squared r dt, which is otherwise known as r double dot, is equal to minus L over m, L u squared over m, second derivative of u with respect to theta squared. So that's equal to minus L squared u squared over m squared d squared u d theta squared. Alright, now at this point you should be going, what the hell am I going to do with this? I'm going to go back to my ugly looking equation, copy it, and replace terms. Minus L squared u squared over m squared d squared u d theta squared. Minus L squared over m squared u cubed is equal to minus g m u squared. Alright, I'm going to replace r with 1 over u. I'm going to replace r double dot with minus L squared u squared over m squared d squared u d theta squared. Makes the there? Ah, it cancels out, right? So I have MA is equal to GMM over R squared. So little m cancels out. Little m would be the mass of the planet. The big M is the mass of the sun. The mass of the planet is kind of cancelled. Okay, so wow. I can divide through by U. So this is the same thing as d squared u d theta squared plus u is equal to g m squared over L squared. If I just sort of move all the terms around. And I have discovered that I can write my differential equation for R through the second law as a linear second order inhomogeneous differential equation where the inhomogeneous term on the right hand side is constant. And once again, the correct answer to what have we discovered is that our motion is that of a simple harmonic oscillator. This is just tremendously clever. People, see, TV is ruining young kids' minds. If you all grew up in the 1800s, you would be in grammar school figuring this shit out. Alright, I mean, look, you know, we're the beneficiaries of 200 years of people figuring out how to do things. Alright? Alright, so, here's the solution. Actually, you can do even better than this. If you let W be U minus G M squared over L squared, then dW d theta squared is equal to d squared U d theta squared. And I can yank all that stuff all over there, and the second derivative of W squared theta squared plus W is equal to 0. So it really does look like a simple harmonic oscillator. And so W of theta is some amplitude cosine of theta plus delta is the solution to the differential equation.
No, you never really use. Actually,
And so if you unpack it, one over R is equal to G M squared over L squared plus A cosine of theta plus delta, which we're going to write as 1 over capital R, 1 plus epsilon cosine of theta plus delta. I really want to know where they went. In the old building, they had in the display cabinet a cone that had a bunch of planes put through it. People remember what I was talking about? That showed the conic sections of a cone. So you take a cone, and you think about all the ways you can slice a cone. One way you can slice the cone is straight across the cone. The cross section is a circle. One way you can slice the cone is at an angle that doesn't go through the bottom of the cone. The cross section is an ellipse. One way you can slice the cone is vertically downward. The cross section there is a parabola, and one way you can slice the cone is this way, but you hit the bottom, and that's a hyperbola. The cross section is a hyperbola. And the 4 types of cross sections of a cone are R as a function of theta. Are 4 possible solutions you can get out of this if you let epsilon be exactly -1, more than -1, no, 0, positive, and more or less than -1. Is that the right answer? Where's the book? I got a book. Look at chapter like 7. There's a so all this is in chapter 7. Take it back. It's all in chapter 8. So if epsilon is 1, it's a parabola. If epsilon is 0, it's a circle. If it's between 0 and 1, it's an ellipse. If it's greater than 1, it's a hyperbola. So we've proven Kepler's first law. Through the middle?
Epsilon.
That's a good
What is
question. I don't know
what is
happens.
epsilon actually supposed to be then?
So epsilon's called the eccentricity.
That word sounds familiar.
Okay, so the eccentricity of the orbit is how non-circular the orbit is. If an orbit is exactly circular, the eccentricity is 0. If the eccentricity is small, it's between 0 and 1, the orbit is elliptical. The more it gets close to 1, the more it becomes basically, well, the ellipse opens up, and epsilon equals 1 becomes a parabola figure. And then when epsilon is more than 1, it's a hyperbola. Okay? So, we started with Newton's second law, F equals ma. We figured out how to write A. So all of this crazy work up here, where we start with, you know, R is R hat, then we take the derivative of it. The goal is to get down here and find a formula for the acceleration. Then you take that and you stick it into F equals ma, where you know Newton's second law. So you know Newton's second law, you know the gravitational force. Then you get a differential equation which is ugly. Okay, you can numerically solve it. We give you theta as a function of c. But if you want, you can algebraically solve it or analytically solve it if you are willing to accept r as a function of theta. So this is a funny solution, right? What it tells you is, as you go around, how big your radius is at different angles. So instead of saying, where am I at a given time, r is a function of t, you say, where am I as I go around? What's r as a function of theta? Alright, so you think about what that harmonic oscillator thing is doing there. If you have an elliptical orbit, r as a function of theta is big. So let's suppose I got an ellipse that looks like this. R as a function of theta is big, r as a function of theta is small. R as a function of theta becomes big and bigger. R as a function of theta becomes small. So you bounce back and forth between two r values. Basically, you oscillate back and forth between two different r values.
Where'd you pull up the R?
The big R here, well, I guess what you do is you divide by, alright, so you pull this stuff out and you make the epsilon. I'll give you the definitions, right? So big R is L squared over G M little m squared. Epsilon is AR. So you just stick those back in there, you'll get the same result we had before. Yeah. And delta is a phase again. That if you just says where you start, basically. It's not the phase is not interesting until you start talking about the precession of the perihelion. So it turns out that planets don't orbit in ellipses. That because there are other planets, the ellipse doesn't, you don't come back around to exactly where you started. When you get back out to your biggest R, you move up a little bit. And so your ellipse then comes up here, then you do an ellipse kind of like that, then you do an ellipse kind of like that, then you do an ellipse kind of like that. And so Jupiter, because it's a big massive planet,